All right. Our next speaker is Kaavya, who's a PhD student in applied physics at Yale University. And she's going to present to us on improved non-local magic state cultivation on the folded surface code.
I hope I'm audible. Right. Yeah. Thank you for the introduction and the opportunity to speak here. Today, I will be talking about ongoing work in Shruti Puri's group at Yale. This is on the topic of producing high-fidelity magic states with low space-time overhead. Before I begin, I'd like to thank all my co-authors, and especially Katie Chang and Kaavya Sahay, who have led this project along with myself. So let me begin by motivating and describing what magic states are. So here on the top of the slide, you see a small quantum circuit. This has a C0 and a Hadamard. These are Clifford gates. It turns out that you can generate a quantum circuit of any size, and as long as it has only Pauli or Clifford gates, this is in fact efficiently classically simulatable. So you cannot get quantum advantage from such a circuit. In order to get quantum advantage, you have to insert non-Clifford or magic gates, as Ken complained about earlier. And so, in order to get quantum advantage, you need these gates. But one thing to remember at this point is that these gates are not being performed on bare qubits when we're performing fault-tolerant quantum computation. These gates are all being performed on encoded states in quantum error-correcting codes. And the idea of this particular code here, which is, as an example, the rotated surface code with a distance d, is that it is fault-tolerant to up to d by 2 errors. So if less than d by 2 errors happen on it, it is correctable. This property is also followed by the Clifford and Pauli gates you see on the circuit on the left. However, it turns out that if you try to do a T-gate on an error-correcting code such as the rotated surface code, it is no longer fault-tolerant because you cannot perform a T-gate transversally on this particular code. There have been ways that have been proposed to get around this problem, and that is to transform the problem of performing a T-gate into that of teleporting an existing T-state onto your logical qubit. So here you have a T-state, and you use Clifford gates to move the T-state information onto your logical qubit and then measure out the original qubit which had the T-state. So in effect, the problem now becomes, instead of having to perform a T-gate, having to produce a high-fidelity T or magic state. And specifically, the fidelity of this T-state should be equivalent to the fidelity of the Pauli states that we were producing earlier on in our Clifford circuit. Once you've defined the problem, let's look at previous attempts to address it. And in the context of our physical hardware today, our physical hardware has errors that occur about 0.1 to 1% per operation. But in order to reach the desired fidelities, we want a T-state that has an infidelity of about 10 to the minus 9 or much, much lower for certain applications. And until very recently, the state-of-the-art way to do this was called magic state distillation. And the idea here is that you take several copies of erroneous T-states, magic states, and each of these magic states could have the wrong logical state encoded into the error-correcting code with a probability linear in the physical error rate of your components. And you feed all of these magic states into what is called a distillation circuit, and what is output from this distillation circuit is a magic state of higher fidelity or lower logical error rate. Specifically, if you use the 15-to-1 distillation circuit, you obtain a magic state that has infidelity suppressed cubically. So now your logical error rate is p cubed instead of the original p. If this p cubed logical error rate is not enough for you, you could choose to perform several copies of this distillation circuit and feed the resulting output into another layer of distillation to get a p to the 9 suppression of the logical error rate. So as you can see, magic state distillation allows you to reach arbitrarily high fidelities by further layers of concatenation. However, because each layer of concatenation requires, in this example, a 15-fold increase in space-time overhead, it is highly resource intensive. And this, in fact, is where magic state cultivation enters the picture, with its original proposal by Gidney and co-authors in 2024. The basic idea of magic state cultivation follows 3 steps. The first step is to inject your magic state into a small code of distance d1. And as this is just a basic injection step, at this stage, your logical error rate scales linearly with the physical error probability. The second step is the cultivation step. And what this involves is performing repeated logical state checks on your distance d1 code. Basically, you're checking whether the state you actually encoded into the code is the state that you wanted to or not. If any of these checks fail, you discard the small code and you restart the process. In the situation that your checks all succeed, there are 2 possible outcomes. Either you've actually produced the state you wanted to, or there are at least D1 errors that occurred in order to give you the impression that you've succeeded while failing. So this is good because our logical error rate now scales as p to the d1, where d1 is the distance of our smaller code. However, our smaller code is, in fact, just a distance d1 code, and therefore cannot correct d1 errors, but only can correct up to d1 by 2 errors. And so this state is, as Gidney refers to it, too good for the code it is currently encoded into. It is, in fact, a fragile state. And at this point, the need of the hour is to quickly grow into a larger code with distance sufficient to predict this p to the d1 fidelity. And this larger code, we say, has a distance d2, which is at least twice of d1. On this larger code, we can now continue doing error correction. And error correction during decoding gives us soft information. And if this soft information indicates to us that it is likely that a logical error may have occurred on the larger code, we can choose to further discard this larger state and get even lower logical error rates. So this is the basic outline of magic state cultivation. And I'll give a brief overview of the results that people have obtained so far and put our work in context. So we have the initial state psi, the original D1 code. For now, we'll fix the distance D1 to be 3. All the protocols that we're discussing today, including our own, choose the D2 code to be the rotated surface code. There are several reasons for this. The rotated surface code has relatively low space-time overhead. It has easy to understand and implement logical gates, and the decoders are fast and accurate. And then each of the protocols that we're kind of addressing today also have their own trade-offs in terms of performance. For Gidney, he starts off by encoding the T state, which is the eigenstate of the Hadamard operator, and he encodes this into the D1 code being the color code. Because he's growing from the small color code to a larger surface code, he has to perform a protocol that is referred to as grafting. And it turns out that the error correction and decoding of grafting is quite difficult and does not perform as well as we'd like it to. In order to circumvent this, a subsequent proposal by Vaknin chooses to use the D1 code to also be the rotated surface code. But they also encode a 2 logical qubit magic state, which is the eigenstate of the C0 operator. Because this is a 2 logical qubit state, it is overall more prone to errors and has a slightly higher logical error rate and space-time overhead than the original proposal. Another proposal by Chen and co-authors once again encodes the Hadamard eigenstate and does it on a smaller D1 code, being the surface code variant that they propose, calling it the RP square surface code. This does not use a larger magic state. However, in order to perform the logical checks during the cultivation stage, they have to perform code morphing operations, which use increasing number of noisy gates, therefore introducing additional error mechanisms at the fragile cultivation stage. To put these previous works in context, this is the performance that they show for the D1 cultivation schemes. On the y-axis, we have the logical error rate. And if you look at the top point, which is about 2 into 10 to the minus 3, that is the logical error rate you obtain after the complete injection plus cultivation plus escape protocol for your distance D2 code. What is happening as you move down towards the right is that you're post-selecting and more soft information that is obtained from error correction of the D2 code, telling you whether it has likely had a logical error or not. And therefore, you're able to see a substantial reduction in the logical error rate from over 10 to the minus 3 to 10 to the minus 6. Of course, because you're discarding these large states, your space-time overhead increases, and that is the x-axis, the number of expected attempts you need to try this protocol before you get a shot that succeeds. And so to reach these lower logical error rates of near 10 to the minus 6, you have to try 3 or 4 times in these particular protocols. In our work, we propose using the Hadamard eigenstate as the same as the previous protocols by Gidney and Chen, but we choose to do it on the unrotated or the regular surface code, therefore avoiding bottlenecks encountered by previous protocols. And the results we see are as follows. This is preliminary. So at the top of the curve that we have here, we already see a lower logical error rate in comparison to previous protocols. And as we perform post-selection based on decoding of the larger state, we see that our logical error rate drops quite sharply. And we're able to reach competitive logical error rates at much lower expected attempts per kept shot than previous protocols. So now that we have an idea of what our protocol is and how it performs, I'm going to break it down and go through it step by step. The first step is injection of the Hadamard eigenstate into the unrotated or regular surface code. This is fairly simple. We take a product state of unentangled qubits, where one of the qubits is in the state that we want to produce in our regular surface code, and then perform a unitary circuit that eventually produces the unrotated surface code as its output. In order to see the error rate of this entire process, this injection process, we can see that if an initial error happened to our important qubit, the qubit that had the Hadamard state at the beginning, the entire surface code would then be encoded with the incorrect logical state, therefore showing us that the injection process has a logical error rate scaling linearly with the physical error rate. The second step of our protocol is performing these logical checks on our regular surface code. And to see how we do this, we can see that it is a specific example of the Hadamard test, where in order to check the logical operator H here, we prepare an ancillary state and perform controlled H checks on our encoded state before reading out the ancilla. If the state that we wanted to check was actually in the +1 eigenstate of the Hadamard operator, then our ancilla would give a +1 outcome on readout. If it was not, then hopefully we would see a -1 outcome. We could choose to do this controlled Hadamard check on our regular surface code using a single qubit ancilla, but this turns out to not be fault tolerant. And so we choose to do it using a 3-qubit ancilla state. Additionally, we need to see what a Hadamard operator looks like on our surface code, and it looks like the following. It is not, in fact, fully transversal, i.e. a H on all of the individual qubits, but it is a series of single qubit Cliffords along the diagonal, and also controlled Z gates across the diagonal. So it is a full transversal operator. The protocol for performing this logical check is as follows. We first take our 3-qubit GHZ state, and we perform controlled Clifford gates on our diagonal qubits. We can then perform controlled Control Z gates on our off-diagonal qubits. Note that both of these sets of gates are non-Clifford gates and therefore are not classically simulable. Once we've covered all the qubits in our regular surface code, we have successfully performed the control Hadamard logical gate. But what we now need to do is read out the GHZ state. We perform a disentangling circuit on our GHZ state, and obtain flags for our GHC qubits along with the CH measurement outcome. If there are any errors, our GHC flags may flip, and our H measurement outcome may also flip, giving us -1 outcomes. In the presence of any -1 outcomes, we choose to discard the state and try again, and we only pass on the state to the next part of the protocol if we get all +1s at this stage. The next part of our protocol is an interim growth and post-selection stage. So at the moment, we are at the regular surface code of this distance 3. And what we do is we apply a short depth unitary to grow into a rotated surface code of distance 5. And this particular short depth unitary is explored in more detail by my colleague Peikai in an upcoming work. The procedure to do this is as follows. We introduce ancillary qubits in between our stabilizers of our existing surface codes and perform 2 gate layers, 1 and 2. As a side note, these gate layers are in fact just the first 2 steps of stabilizer measurements on your regular surface code. But at this point, the state of the entire system of our unrotated surface code and our ancillary qubits is in fact the distance 5 rotated surface code. At this point, we choose to perform stabilizer measurements on our distance 5 surface code, and again, discard the state if we have any stabilizer measurements which return us the -1 outcome, indicating the presence of errors. At this point, we now have a logical error rate that scales hopefully as p cubed, but the distance 5 surface code cannot correct for 3 errors. It can only correct for 2 errors. And so the need of the hour is to escape into a larger code as quickly as possible. There are several ways to do this, and the way we choose to do so, the way I'll talk about today, is an extension of the unitary circuit that I just talked about in the previous part of the protocol. We transform our rotated surface code from a distance 5 rotated surface code to a distance 5 unrotated or regular surface code using another version of the short depth unitary. So we add in ancilla qubits and perform 2 gate layers. And at this point of time, our system is now a distance 5 rotated surface code. And we can use the same short depth unitary that we just used in the cultivation part of our protocol to grow this distance 5 regular surface code into a distance 9 rotated surface code, and so on if we desired a larger code state size. So this brings us to the end of our protocol from injection to escape. What we can then do is that we perform error correction on this distance D2, which is here 9 surface code, and perform decoding, out of which the decoder gives us soft information, which tells us how confident it is in the logical status of our surface code. If it has a very low confidence level, then we may choose to discard the state, therefore increasing the fidelity of our output. There are fundamental challenges to evaluating the performance of magic state cultivation protocols. And they are as follows. If we look at the first 2 stages of our protocol, they involve non-Clifford gates, which are not efficiently classically simulatable. In fact, you have to use state vector simulations to figure out how they perform. And state vector simulations scale as 2 to the number of qubits that you have in your system. Because the first 2 stages have support on fewer numbers of qubits, relatively speaking, this is currently feasible. However, if we try to use a state vector simulation to figure out the performance of the entire protocol from end to end, this entire protocol involves about D2 square qubits, where D2 could be 9 or 17 or higher. And so it is not classically feasible to simulate a 2 to the n, where n is 100 or 200 size system. And so as a result, what previous protocols have resorted to is that instead of checking the performance of the H eigenstate, they have checked the performance of the Y eigenstate, which is a Pauli state and therefore efficiently classically simulatable. We can perform the same thing, and we see performance as follows. It looks very much like the plot I showed earlier, where we have an initial logical error rate of 10 to the minus 4 into a factor, and then it drops sharply. And you can see that previous works have also used the Y eigenstate. But a question that arises at this point of time is this Y eigenstate performance really truly reflecting how our H eigenstate is performing, which is actually what we want to figure out. And so we can do this by using a handoff protocol that transfers information between the quantum and classical parts of our protocol. The key realization is that because only the first two parts of our protocol use non-Clifford gates, we can take output from the first two parts of our protocol and input it into the next part of our protocol. The output is formatted into two parts. The first is Pauli errors called destabilizers, and the second is a logical state vector that we store in memory. We feed in the destabilizers into the larger Clifford simulator of size D2 square and complete the simulation from end to end. When we do this, we see the following performance. Our results are in the darker pink for the H eigenstate and overlap pretty closely with the Y eigenstate performance, barring some discrepancies at the lower end of the scale. But overall, we see that our protocol still performs better than previous proposals. And in fact, if we were to try 2 attempts of all of our protocols that we have on the slide here, the ones in Gidney's and Chen's previous proposals and ours, you would reach a much lower logical error rate than the previous proposals and get a high fidelity magic state as we desired. So that brings me to the end of my talk. We have demonstrated a high fidelity, low space-time overhead proposal to produce magic states. In particular, this is compatible with non-local architectures such as trapped ions and neutral atoms because it uses a fold transversal gate. Current work that we're still making progress on is adapting this protocol to be tailored to the trapped ion and neutral atom platforms and their hardware constraints. And further, the entire talk I gave today was focused on cultivating a distance 3 magic state where the logical error rate scaled as p cubed. We can extend this protocol to have a fault distance of p to the 5 and therefore reach much lower logical error rates for our final magic state that we're producing, which then can be fed directly into a logical quantum algorithm instead of requiring a subsequent layer of distillation. And with that, I come to the end of my talk, and I welcome questions. Thank you.
All right, questions?
Great work, Kaavya, as always. When you do these non-Clifford operations, are their failure rates all the same, or do you have like a higher penalty for monopoly versus?
That's a great question. At the moment, in order to compare fairly against previous proposals, we're using an error model where every operation has the same failure rate, because this is what previous proposals have used. As we go further into the flexible architecture comparison, we're going to use more realistic error rates and see their performance.
Then you'd agree, since you're doing verification, it's part of RC1.
Yeah. Thank you.
In your preliminary results, like in your plot, the plot starts going up after a while?
Great question. Oh, sorry, it's just bugging out. There we go. So that is an artifact of sampling issues. It is not actually going up. These are, the short answer to your question is that we just need to collect a lot more samples and then it will level out. Whenever I've performed these simulations and I don't get enough samples, because of the way that the gap post-selection calculates its error bars, it has a false artifact of appearing to go up. But it shouldn't appear to go up when you have enough samples.
Do you think it is going to saturate? Or?
It will saturate. I don't know whether it's going to saturate at the point that it appears to be lowest, or it will be lower.
Yeah, I believe if I remember correctly, in the original Gidney work, he kind of posits without much support that this Y state should have approximately twice the logical error rate as the T state. It looks like your results like roughly support that. Do you have any intuition as to like why?
So just to maybe broaden the context, I believe in Gidney's work, he actually does perform a simulation of the Y state and a state vector simulation of the initial 2 stages of the T state. And therefore, he sees that at around 10 to the minus 3 physical error rates, it's a factor of 2. That factor does change the lower he goes in the physical error rate. So that's not really a deterministic factor by any means. I also believe that to the second part of your question, that does not directly apply to this particular scenario. It looks like a factor of 2, but on examining the circuits in more detail, what we found are that there are certain error mechanisms in the Y state preparation that are not there in the H state preparation and vice versa. So they're really just like different plots.
Mm-hmm.
And this is maybe a false equivalence to some degree.
Okay.
This conversion of like when you were growing your distance, how does that scale? Because you went from like 3 to 5 and then 9. So it does roughly double every step?
Yes, the unitary growth that my colleague Pekai is working on, it always goes from a distance D code to a distance of 2D minus 1. So it's doubling every time.
Can you go to the slide where you do the CCZ gates?
Mm-hmm. I'll just...
Yeah, okay. Yeah, I guess I was just a little confused that if you have like errors in your like the insula, would they propagate to?
Great question. So this is exactly why we use a 3-qubit GHC state. If you used a 1-qubit GHC state, then you can imagine that any error on the ancilla would spread to the whole surface code. But because we're distributing the ancilla state to be a 3-qubit GHC state, an error on one of the qubits may spread to part of the surface code, but it hopefully does not create, we've designed it such that it does not create a logical error. And because it's on part of the surface code, there's a subsequent round of stabilizer measurements which then detects the presence of this non-logical error.
I also had a question. So you're doing 2 stages.
Yes.
Does it make any sense to try and do a 3rd stage?
This is something that we're still actively investigating. This is a protocol that we found that works. It may be that we could still optimize it.
Thank you.
Yeah.
All right, let's thank the speaker one more time.